Welcome to this FP2 video on further loci in an Argand diagram. So we're going to look at two things in today's video, and this is the first. Now, where we get this from, I'm not going to go into too much detail, but it's basically to do with ratios. Okay, so the distance from one complex number to another complex number in the ratio, because that ratio remains constant for all points, it basically creates a circle. Okay, like I said, there's a bit more details if you want to look in your textbook as to where this comes from. But today we're just going to go about how we use it. Okay, so the first thing is to recognize that this is going to produce a circle, and then I'm going to show you how to deal with that. As always, it's always easier to show you with an example, so here we have an example. So first, I'm just going to write it down again. So this is what we've got. And then I'm going to replace the z with an x plus iy. So that's going to become x plus iy plus 7i minus 7i equals 2 x plus iy minus 10 plus 2i. Next, I'll collect my x's and my essentially y's, my real parts and my imaginary parts. So that's x plus 2 plus y minus 7i. And then this is x minus 10 plus y plus 2i. Oh, missed out an equals in there. Now, next step is to square both sides. Now, that will enable us to remove the moduli, the modulus signs from both sides. So we're left with x plus 2 squared plus y minus 7 squared equals 4. And then x minus 10 squared plus y plus 2 squared. Now all that's left is to expand and then collect the like terms. So we've got x squared plus 4x plus 4 plus y squared minus 14y plus 49 equals, and then I've got 4 times x squared minus 20x plus 100 plus y squared plus 4y plus 4. Oh, didn't need to start so far to the left after all. So that's 4x squared minus 80x plus 400 plus 4y squared plus 16y plus 16. Now, I think the easiest thing to do is to take everything to the right-hand side. So that gives me 3x squared, because I'm taking away x squared. Then I'm going to take away 4x, so that leaves me with minus 84x. Now currently I have 416 on the right, and on the left I have 53. But I'll leave that constant for now, and I'll just do the y squared, so plus 3y squared, and then I'm adding 14y to my 16y, so that's 30y, and then my constant is going to be 363. and that equals 0. Then I can divide by 3, so we get x squared. 84 divided by 3 is 28x. Y squared plus 10y, and 363 divided by 3 is 121. Now what I need to do is complete the square for both my x and my y. So x minus 14 squared minus now 14 squared is 196 plus y plus 5 squared minus 25 plus 121. And then adding these three up gives me minus 100 on this side. So taking it to the other side gives me 100 x minus 14 squared plus y plus 5 squared. And you'll recognize that as the equation of a circle. Okay, so these two are going to give you the locus of equation of a circle. Now we need to, for this purpose here, state in its center and radius. So center 14 minus 5, radius 10. Now that was part A. Part B now is to sketch the locus of Z on an Argand diagram. So here is my sketch. It has a center of 14 minus 5, has a radius of 10, so this one will be, plus 5 up here. This one down here will be, minus 15, and then that'll be 4, and that will be 24 in terms of the x values. So that's kind of roughly how this looks. In terms of the original complex numbers, minus 2 plus 7, so it's going to be up here somewhere, so let's call it kind of there for A, and the other one's plus 10 minus 2, so somewhere like there for B. Okay, and then basically the ratio of these to any point on the circle, point P. So as I go around this circle, this length and this length, while changing, remain in the same ratio. Okay, so as P goes around, this length and this length stay in the same ratio. Okay, the red bit, is just for me to explain, nothing to do with part B in terms of the question. But hopefully that makes sense to you. And like I said, there's a bit more information in your textbook to where this comes from. So if you're interested, I suggest you read that. And if you want more, comment down in the comments of the video, and I will maybe make another video just explaining a bit more. But what I'm really focusing on these videos is just being able to get you guys to do it, because I think sometimes we can focus a lot on the understanding, but for some things it's worth being able to do it first and then get the understanding afterwards, and some things it's worth the understanding first and then being able to do it afterwards. So we kind of approach it in two different ways. But anyway, that's the first type of thing I wanted to show you today. The next is to do with angles. Now, for the next bit that we're going to look at, we want to start off with arg z minus z1 equals theta. So you know that this is basically a half line like this, okay, where this is Z1, you know, and this particular value at the end of the start of the half line, or you know, halfway down what would be the full line, where this point it doesn't is not included. Okay, so I didn't on the previous ones, but we do often show that as an open circle, just to show that it's not included. Okay, and this is just on an Argand diagram. So we're going to use this along with some circle theorems. So if you remember from your circle theorems, if I've got a circle and I've got, you know, 2 points at the end, then an angle made by joining these 2 points A and B, so this angle here, will be the same as the angle made by joining A and B to another point on the circle. These angles stay the same. So we're going to be using this along with angles in a semicircle. Okay, so the point on the edge there, it makes a 90-degree angle, and angles from A and B to the center and to the edge. The edge one is half the size of the center one, or the center one is twice the size of the angle at the circumference. So we're going to be using basically these, and they give us that arg z minus a over z minus b is equal to theta. Now, I'm not going to go through how we get to this again. You know, I'm just going to go about how we use it. So I've got two complex numbers with their angles, so they're half lines. Okay, alpha and beta, and then this angle here is going to be where theta is. So that's going to be theta, and this will be the point P. Now, just for the purposes of this angle here would be equivalent to beta, and this angle here will be equivalent to alpha. So theta is, you know, alpha minus beta, if you will. So theta is alpha minus beta. And what we end up with in this case is not a full circle, but an arc. Now, if theta is less than pi by 2, the locus is the major arc. If theta is greater than pi by 2, the locus then is the minor arc. And if theta equals pi by 2, then the locus is a semicircle. Okay, so that's just a little bit of kind of information for you. But as you can see, in terms of my A and B, A is the top one, B is the bottom one. And then if this, we generally draw these kind of anti-clockwise. So in this case, this angle appears to be less than pi by 2, and this would be the major arc, as you can see there. Okay, if this was bigger, these two would be further apart, and then it would the drawing would be of a minor arc rather than the major arc. But that's kind of roughly how it is. Now, what we need to do here to find the center of the circle on which either the major arc or the minor arc is located, we basically need to do algebra with, usually some geometric work in, or you can kind of just use some geometric work in. But let's have a look at that in the next example. So here we have our example. So arg z minus 3i over z minus 5 is equal to pi by 4. Okay, so we've got to sketch this. Now, before we jump into the sketch, let's have a look at a few things. So arg z minus 3i over z minus 5 is going to be the same as arg z minus 3i minus arg z minus 5, and of course that equals pi by 4. So if we let L1 be the half line satisfying can't spell satisfying there, arg z minus 3i equals alpha, and then L2 will be arg z minus 5, which is beta, and then of course alpha minus beta equals that pi by 4. Now in terms of a diagram, A will be here, this will be A at 0, 3, and B will be somewhere on this axis at 5, 0. Now, in terms of how these will look, we'll obviously have a half angle coming off them. So this is my initial diagram. So that's alpha, that's beta, and that is theta. And theta is, of course, pi by 4. Now, as you can see from my kind of information up here, alpha minus beta is pi by 4. So alpha is bigger than beta. But in my diagram here, alpha is clearly smaller than beta. So what that implies is that where I've currently got this P is in the wrong place, because we need to have alpha being larger than beta. So we need to change this diagram now. So rather than it be above A and B, let's put it below, like above the axes, the x-axis. Let's now try it below the axis. So let's, put it down here. So now if I join my lines to P down here, and then from A like so. Now alpha is here and beta is here, and this is obviously still pi by 4. So now what we've actually got is that arg z minus 3i is minus alpha, and arg z minus 5 is minus beta. So instead now we've got minus alpha minus beta equals pi by 4. So we actually have beta is pi by 4 plus alpha. So that's kind of our scenario now. Okay, and it's just from this diagram, so we know that instead of it being above the x-axis, it's going to be below the x-axis. Okay, but it's I think it's hard to kind of always spot. You always got to go anti-clockwise from A to B. This could have been a minor arc, but it's going to be a major arc. In this case, your alpha is bigger because it's a smaller negative value than the negative of b. So it is larger, but this will be the scenario at the end. Okay, beta is equal to pi over 4 plus alpha. So going back to my original diagram, we're getting our circle on there because it's going to be a major arc down the bottom. And then this can be rubbed out. So this is the scenario that I am left with. So if I join it back up to, roughly where we had P in that diagram to the right, I've got like this scenario going on. Okay, where this is pi by 4 and this is beta and this is alpha. Okay, so that's what I've got. This is P and it's an X and Y coordinates. And then this will be like as this moves around, the ratios will change, but this, alpha and beta will change, but pi by 4 will remain the same. And in this scenario, beta will be equal to pi by 4 plus alpha. Okay, so that's kind of what's happening there. All you need to know really when you get these is whether it's going to be, above here or below there. Okay, basically when you've got the two points which will produce the half line, you want to know if it's, if you imagine joining these two together, you want to know whether it's that side of the line or that side of the line. Okay, so you always assume it's like this side of the line first, and then look at the diagram, and then you can work out if it's not that side, then it must be the other side. Okay, so you deal with it when alpha and beta are positive angles, so up here somewhere. And then if it doesn't work for that, then it must be the other scenario. Okay, so we're left with a diagram like this. So this now is the locus of Z. Oh, showing the locus of P, I should say, which is represented by Z. Okay, so there's that. Now let's look at finding the Cartesian equation of this locus. So for part B, find the Cartesian equation of this locus. Show your reasoning clearly. We're basically going to find the equation of this circle and then set some sort of limits just to avoid this minor arc here. Now you can solve it geometrically or algebraically, and geometrically I tend to find that if these two have like a common X or a common Y value, then geometric is the way to go. So, like in this case, if both of these were on the Y axis or both were on the X axis, then it would be pretty straightforward because, we've got like the center of the circle here, which will be pi by 2, double the angle. And then if we set out this triangle here, if these were on the same line, the A and the B, then finding this length and this length would be dead easy. And that will enable us to find the radius and the center quite quickly. Okay, but in this case, they're not on the same, the same either X or Y value. Okay, which makes our life a lot harder to do it this way. Okay, so for this particular question, I will use method 2 algebraic. But just to show you, if they were on the same line, so imagine A was here at 0, 3, and imagine B was on this y-axis here at 0, -5. And then the center was somewhere over here, the arc of the circle was there, the center was here. And this was pi by 2. Okay, it then becomes quite quick and quite easy because we've got, a total length here of 8. This radius and this is a radius, so they will stay the same. But the total length here of 8 would mean that this line here would meet at 0 minus 1. Yeah, because that'll be 4 and that'll be 4. And then we can use like trigonometry. So sine this small angle here will be pi by 4 because these two are radiuses, aren't they? So, call that r for the radius. So sine of pi by 4 is opposite, which is the 4 over the radius. So the radius is 4 over sine of pi by 4, which would mean that the radius would be 4 root 2 in this particular example I've got in red. Okay, and there's various ways, you can do it using Pythagoras and stuff like that. So geometric, I think, is the way to go when they are, either both on the x-axis, both on the y-axis, or both of a common x or a common y. Otherwise, I would say to go with the algebraic method, which is what, like I said, I was going to do in this case. So z minus 3i over z minus 5 is x plus iy minus 3i over x plus iy minus 5, which is x plus y minus 3i over x minus 5 plus iy. But actually, before I write that, I'm just going to rub it out. I'm going to write that at the end. Because what I need to do is, to deal with this fraction, I need to multiply by the bottom, the denominator's complex conjugate pair, or z minus 5, if you remember, with a little star above it. So that's what I'm going to be multiplying by. So x plus iy minus 3i over x plus iy minus 5 multiplied by, now the real parts stay the same and the imaginary part changes. So in fact, if I write this bottom one just like minus 5 plus iy, then it'll be x minus 5 minus iy, x minus 5 minus iy. So that's what I'm going to be multiplying by. So that gives me x squared on the top minus 5x minus, I don't really need to put the next bit in, but it's xyi. Then I've got plus xyi minus 5yi, and then plus y squared, because minus I squared y squared will become plus y squared. And then I've got minus 3xi plus 15i minus 3 plus 3y I squared, which is minus 3y. And the bottom will just be x minus 5 squared plus y squared. So just dealing with the top, I've just got x squared minus 5x. These two will cancel with each other. Plus y squared. And then I've got minus 3y minus 5y I minus 3xi. Oh, and plus 15i. All over x minus 5 squared plus y squared. So separating out the real and imaginary parts, we've got x squared minus 5x plus y squared minus 3y, and that is over x minus 5 squared plus y squared, plus 15 minus 3x minus 5y multiplied by I over x minus 5 squared plus y squared. So arg of that equals pi by 4. Now, because it's pi by 4, in this case, tan of... So let me take a step back. Because we've got this pi by 4, and the tan of pi by 4 would mean that the real part and the imaginary part of my triangle would both be the same size, wouldn't they? It would be an isosceles triangle. So if I've got this is the real, this is the imaginary part, and this is theta. And tan of theta is the imaginary divided by the real. And tan of theta is pi by 4. Tan of pi by 4 is 1, so that the imaginary part and the real part have got to be equal in this case. So I can now say, therefore, x squared minus 5x plus y squared minus 3y over x minus 5 squared plus y squared equals 15 minus 3x minus 5y over x minus 5 squared plus y squared. And I obviously can get rid of that I because I'm just talking about the values. Now, these two fractions have the same bottom value, the denominator, so the top, the numerators must be equal. So I get this. Now, taking everything to the left, I get x squared. Now I'm plussing 3x, so that's minus 2x plus y squared, and I'm adding 5y, so that's 2y, and that equals 15. So completing the square, x minus 1 squared minus 1 plus y minus 1 squared minus 1 equals 15. So x minus 1 squared plus y minus 1 squared equals 17. So there we are, centre 1. Oh, sorry, this is not minus, it's a plus, isn't it? So centre 1 minus 1 radius root 17. So that is the Cartesian equation of this locus. And all that's left is to apply some limits. So this would be, so I'll put it here, where x is less than 0 or y is less than 0. Okay, because what that should do is, if I've got this diagram, then when x is less than 0, so when x is this side of the axis, y can obviously take any value, positive or negative, or when y is less than 0, so y is below the axis, x can take any value, positive or negative, and that will eliminate this section of the circle then, because, you know, if x is negative, y could be anything, and if y is negative, x can be anything, but it doesn't let me have x and y both being positive, which is in this quadrant 1. Okay, so that is the limit, and that was what we would need to show, because otherwise we're saying the locus is the full circle, and it's not, it's this major arc. Okay, so it's quite a long example. Hopefully you managed to follow it okay. I've just got 3 questions for you to have a go at, and as always the answers will be at the end. But if you've found this video useful so far, please hit the like button, subscribe if you're yet to subscribe, and if you're willing and able to help me out financially, please consider hitting that join button. Now on to the questions. So 3 questions for you to have a go at here, all past paper questions. There are plenty more in your textbooks and online. These are just 3 I've picked out just on the stuff that we've just been doing, 1 on each essentially here, you know. Okay, so have a go at these 3 and check out the answers at the end of the video. Okay, so starting off with plus I equals 2z plus 4 minus 2I. So the first thing I want to do is just replace my z. So x plus I y plus 1 plus I equals 2x plus I y plus 4 minus 2I. Collect the like terms together, so x plus 1 plus y plus 1I equals 2, and then x plus 4 plus y minus 2I. Next we want to square them, so I will skip a line here, but let's jump down to this. And then let's expand them. So x squared plus 2x plus 1 plus y squared plus 2y plus 1 equals 4 brackets x squared plus 8x plus 16 plus y squared minus 4y plus 4. So on the right now we've got 4x squared plus 32x plus 4y squared minus 16y, and then 16 plus 4 is 20, 20 times 4 is 80. And then here we've got x squared plus 2x plus y squared plus 2y plus 2. So taking everything to the right, we get 3x squared plus 30x plus 3y squared minus 18y, and then plus 72. Sorry, that's 78. Now dividing by 3, we get x squared plus 10x plus y squared minus 6y plus 78. Now completing the square for my x's and y's, I get x plus 5 squared minus 25 plus y minus 3 squared minus 9 plus 78. Sorry, plus, this is wrong up here, 26. Forgot to divide the 78 by 3 there. So 26 minus 25 minus 9 is 8. So I've got, if I start up here, I've got x plus 5 squared plus y minus 3 squared equals 8. And that is the equation of my circle. So that shows that it is a circle with centre minus 5, 3. I would put that down. So say therefore P is a circle with centre minus 5, 3. Because that was what was required. And then normally I mention the radius there, but the radius is in B, so radius equals square root of 8, which is 2 root 2, and that's the exact value of the radius. And this is question 1 complete. So question 2 is similar to the last one for part A at least, but then we have a different part B and C. So let's get into part A first. So we've got z mod z equals 2z plus 4. So this is x plus I y equals 2x plus I y plus 4. And then basically want to square it, but I also want to, on the right hand side, just separate out my real and imaginary part. So squaring both of these gives me an x plus y squared equals 4x plus 4 squared plus y squared. So that's 4 x squared plus 8x plus 16 plus y squared. And then this is x squared plus sorry, I've done this wrong on the right. It should just be x squared plus y squared. So 4x squared plus 32x plus 64 plus 4y squared. That's 3x squared plus 32x plus 64 plus 3y squared. Now I need to complete the square. So before doing that, I will divide by 3. Just to make my life a little bit easier. So 0. So this is now x minus 16 over 3 minus 16 over 3 squared plus y squared plus 64 over 3. The y obviously didn't have the y squared didn't have a y, so I didn't have to worry about that. So just carrying on, squared that. Just carrying on at the top, we've got x minus 16 over 3 squared plus y squared. Now 16 over 3 squared, just doing it now, is 256 over 9. Obviously minus that, and then add in the 64 over 3, we get minus 64 over 9. Okay, so that is going to equal 64 over 9. The minus, take it to the other side. Or x minus 16 over 3 squared plus y squared equals 8 over 3 squared. Okay, so now we've got center circle, center 16 over 3, 0, and radius 8 over 3. Sorry, I've just realized my plus 32 somehow became a minus. So this should be a plus, this is a plus, this is a plus, and therefore this is a minus. So just make a little bit of room here. So we've got minus 16 over 3, 0 as the center. Apologies for that. Very easily done, you know, going from the plus here and then writing a minus down here. It's very easy to make simple mistakes in maths, so it's always important you just scan through and double check your answers. Okay, now part B, we need to sketch this on an Argand diagram. So it's going to give me something like this, where the center is minus 16 over 3, 0, and this radius here is going to be 8, 3. The radius is not big enough to span this gap, which is why it doesn't touch the y-axis. And this circle is, of course, z equals 2z plus 4. Okay, so that's part B done. So C is, given that z lies on F, find the range of possible values of the imaginary z. So that is the range of possible values of y. Because we've got it on the real axis, then it's going to be 8/3 up and 8/3 down. So this is just going to be from 8/3 to 8/3. And that's this question complete. Let's have a look at the third one. So A, we're looking for a sketch. So it's from W minus 8i, so that is here, and that will be our A, and W plus 6, so it's at minus 6, so somewhere here, and that will be our B. And this is 0, 8, and this is minus 6, 0. Okay, and then this equals pi by 2. So knowing that is going to be a semicircle. So it's a semicircle going from 0, 8 anti-clockwise to minus 6, 0. So this is going to be our semicircle here. So we've got this, and then of course where each of these half angles hit this locus, this kind of semicircle, is going to be a 90-degree angle. And then the center of the circle is going to be the midpoint of this. So it's going to be minus 3, 4. Okay, so that is now my diagram complete. So that's part A done. Right, part B. Find the Cartesian equation for S. So for this, I could do it algebraically like we did in the example, but this I think now we'll use the kind of geometric method, because from the diagram I already know the center of the circle. So I basically only need to find this length, and this length can be found quite easily, because this is -3, 4, and this is -6, 0, meaning this is -3, 0. So it means this has a height of 3 and a base of, a height of 4 and a base of 3. So using Pythagoras, the radius here is going to be 3 squared plus 4 squared square rooted, which is just 5. So knowing that, then I can say that is x plus 3 squared plus y minus 4 squared equals 25. Okay, so that's using geometry to be able to find the equation of the circle. And geometry is always quicker and easier to find it, but it's not always possible in every scenario. Okay, in this scenario, being a semicircle, that made my life a lot easier. It meant I knew what the center of that circle was straight away, which therefore then enabled me to use this geometric method, even though A and B are on different axes and there's no kind of like link that way. Okay, so that is part B done. Although I do need to add in my limits, my range. So this is for x being less than 0 and y being greater than 0. Notice it's and this time and not or like in one of the previous example, because it's x is negative and y is positive on all of the values on this locus. Okay, and it's not an equals because it doesn't include these two circular points, A and B. So that is B done now, properly done. Now let's do C. Given that Z lies on S, find the largest value of A and the smallest value of B that satisfy A is less than argument Z, which is less than B. So remember that the argument is the angle, if I just copy that there, the angle between the line connecting Z to the origin and the real axis. So if I do it on this diagram in red here, you know, it'll be this line here, or a line like this one, and this angle here. Call that alpha, maybe, or theta. Might be more appropriate, theta. Okay, so that is the argument of Z in this case. Now, the largest possible value and the smallest possible value, you can see here the smallest possible angle, and I'll do this in green, will be this angle here, won't it? Be a 90-degree angle. And the largest possible, and do this in like a kind of pinky purple, will be this angle here, which will be pi, 180 degrees. So that's the smallest angle, that's the largest angle. The smallest angle goes to this 0, 8, so the W minus 8, I, and the largest angle goes through the W plus 6. Okay, so you know the smallest is like let's use Z because we're dealing with the complex numbers. So Z equals 8i, and the largest is Z equals minus 6. okay, which is what I showed you on the diagram. So arg z is going to be between pi and pi by 2. So like I said, the 90 degrees and the 180 degrees there. Okay, having the diagram really helps for this part C. Now part D is state the range of possible values of real z. Okay, so let's do D. Now for this, I just want to get my diagram back up. So I'll just get it back up here and show you. So the furthest point now to the left is going to be here. Now this is a radius of 5, so this will be at minus 8, 4. Or, minus 8 plus 4i. And then the furthest point to the right is this one here, but it doesn't include this one. So when I do my kind of range, the real values will be minus 8 real z, and then 0, but it can't actually be 0 because 0 is that point here, and then we don't include the ends. Okay, the end points of the semicircle, so the points where their half lines would start. So that would be the range there. And that is question 3 done. So these 3 questions I think a lot easier than the examples I've shown you, or certainly the second example. But have a go at a few more questions and let me know in the comments, if you found this video useful and enabled you to answer those additional questions. Okay, otherwise I'll see you in the next video, which will look at regions in an Argand diagram.